Day 133, electric potential energy examples 2, 3, 4, and 5. For the most part, these problems can be split into two categories. There are some exceptions, but for example, the one we're doing in class, number 1, is the point particle example. And there are 4 specific equations with the 4 general concepts here: force and field and energy and potential, that apply to point particles. If it's not a point particle problem, you can pretty much put it into a parallel plate scenario. That's what we're going to do here in this problem. So when you're in doubt, try the parallel plate scenario. As we showed you in class, you have, say, 2 parallel plates that are charged, 2 metal plates. They're two-dimensional, facing each other, and they're charged. One, say, is charged positive, and the other one negative, and there would be a field between them, a uniform field, which I'm not going to draw right now. But in this case, we have a positive particle. It's probably over here on this side. Let's say, we don't really know where it's at, but let's say it's right there. And what they're saying here in this problem is that you're doing work to move it across this field. In other words, you're moving it, say, from that location, let's call that location A, over to, say, location B. And it's going to take work on the part of some external agent to move that particle from that spot, and now we'll just use blue, and we're going to move it over across to location B. We want it over there at location B. That's going to take work, and it tells you how much work it takes. Now, I have the advantage that I know all the equations by heart, but you should have your equation sheet handy when we're doing these problems, because it's going to take you a while to get used to all these equations, and I will give you all these equations on the next test because I don't expect you to memorize them all. But this one is essentially a straight plug and chug into a delta V equals delta U over Q. Delta V is electric potential difference. Delta U is change in potential energy. Now, from first semester, we know that when you do work, you're transferring energy to something, in this case, this little charged particle. And sometimes it manifests itself as potential energy or kinetic energy or actually heat energy. But in this case, you're doing work and you're giving this particle potential energy. So the work done is going to transfer potential energy if I move it from location A to location B. So this is pretty much a plug and chug at this point. I'm looking for delta V, the potential difference. The change in potential energy is going to be the work that you did, 5 millijoules. That's 5.0 times 10 to the negative third joules, divided by the charge that I'm moving, 350 times 10 to the negative sixth microcoulombs. So it's going to be joules over coulombs. So delta V here, delta V, comes out to be 14 joules per coulomb, which is 14 volts. That's the potential difference. That's the voltage. That's what I'm looking for in this problem. Once again, like I said on the previous slide, these problems either boil down to point particle and point particle equations, or if you can't do it that way, try the parallel plate approach. Here's another one. That will be the parallel plate approach. You have 2 parallel plates. I usually like to draw them, like I said. And you have an electron this time. And the electron is being accelerated. So, once again, you don't always start off on the right, but I will start off on the right again. There's an electron somewhere over here near the negative plate, because in this case, nobody's going to be doing work. In fact, the field itself will be doing work this time. And what's going to be happening here is like somebody's going to let this thing go, and it's going to accelerate to the left because it wants to be repelled, or will be repelled by the negative plate, and it will zoom over, speed up, gain kinetic energy towards the positive plate. It'd be like dropping a ball in a gravitational field. It's kind of like dropping the electron in the electric field here. It will lose potential energy and gain kinetic energy. Now the problem says what is the change in potential energy, but it's essentially a very similar problem to the last one, except for we know other quantities. So really, once again, it's a delta V equals delta U over Q. We're given delta V in this case. Delta V is 5,000 volts, the potential difference. So look for those key words in the problems. It says potential difference in the grammar above. 5,000 is the potential difference equals delta U, which we don't know, over Q. Well, this is an electron. And once again, I'll give you this, or you might remember that an electron has a charge of 1.60 times 10 to the negative 19th coulombs. That's a given. It's an electron. It has that charge, always has that charge. It's negative, but you don't need to worry about that right now. We're just looking at how it's moving across this field. Its change in potential energy. I mean, technically, if you want to put the negative in here, because really it's what it's doing, it's losing potential energy. So if you want to be consistent, you could put the negative on there to show you, in a sense, that it's losing potential energy, but it will be gaining kinetic energy. You don't have to do that, but if you do it here, you end up with 8.0 times 10 to the negative 16th joules loss in potential energy. But it says, what's the change in potential energy in electron volts? So I have to convert that now. This is simply a conversion. I'm going to convert from 8.0 times 10 to the negative 16th joules times my conversion factor. 1 electron volt from the in-class notes is 1.60 times 10 to the negative 19th joules. If I do the math here, this comes out to be 5,000 electron volts. That's my answer to part A. And there's no coincidence that it's pretty much given in the problem, because that's why they define electron volts that way, because they're convenient units for problems like this. You wouldn't even need to do the math here if you've done enough of these. You know that if an electron goes through a potential difference of 5,000 volts, it's going to pick up an energy of 5,000 electron volts of energy. So, but that's a unit thing. Electron volts are a unit of energy. All right, now part B. In part B, we need to figure out the speed, its final speed, when it gets basically to the positive plate. If you recall from first semester, basically this is going to be will be a conservation of energy problem. The particle, the electron, is going to pick up kinetic energy. The kinetic energy formula is 1/2 Ke is equal to 1/2 mv squared. The particle starts from rest, so what's going to happen here is that it will pick up this much potential energy, because it's like a ball falling to earth, and it's going to gain that much kinetic energy. So that will be the gain, or the final kinetic energy of the particle. Just plug that into this kinetic energy formula. So we're going to have 8.0 times 10 to the negative 16th equals 1/2 times the mass, given as 9.11 times 10 to the negative 31st, quantity squared, times v squared. All right, I go to my magic box, my calculator, and it comes out to be v, the final velocity, 4.2 times 10 to the 7th meters per second. That's the speed of the electron as it strikes the positive plate. Example number 4. Electric potential or electric potential energy. Here we have parallel plates once again. It says 2 charged metal plates, so it's pretty obvious what we have in this case. Once again, do not apply the point particle equations to parallel plates. Only apply the point particle equations to point particles. So we have 2 parallel plates charged, and you don't have to be charged, but typically they are charged, otherwise you don't really have a problem or something that you can solve. The field would be 0. But they tell you in this case that these things are 5 millimeters apart. That's the distance. That's d. It's how far they're apart. They're real close together. And they have a potential difference of 85 volts. Now, once again, as I've said before, I have the advantage. I know all the equations. If you go back and look at your equation sheet, we have this particular equation. Delta V for parallel plates equals ED. All right, we're trying to find the electric field strength. We're trying to find E, because that's what this means here grammatically. Electric field strength is E. So basically it's E. This is the way it's usually defined, by the way. E equals delta V over D. So simply just plug in. I'll do it over here. Delta V here is going to be 85 volts. That's good units, proper units already. But D needs to be in meters. That's 0.005 meters. So that's volts and that's meters. And that's why sometimes electric fields are defined in volts per meters instead of newtons per coulomb. They are equivalent to one another. You can prove that. But bottom line here is this comes out to be 17,000. You could say volts per meter, or you could say 17,000 newtons per coulomb. It's the same unit. Equivalent answers. You'll see it both ways. So that's a straight plug and chug problem. One more example now with parallel plates. This time we're going to put the parallel plates horizontal, something like this. And there's a reason you'll see that here, because it's implied in the wording of the setup of this. And I know, though, that here it's really important to get the positive plate on top, which I'll explain as I go along here. In the other problems I was doing, numbers 2, 3, and 4, it didn't really matter which one was positive, which one was negative. It was kind of just my convenience, or just had to pick a direction. But here, I know they have to have like a parallel plate, like a plate horizontal to the ground facing up. It's negatively charged because it says I have a negative particle in here, not necessarily an electron, but something that has extra electrons on it. It has a net charge, a net negative charge, but that charge is sitting there between those two plates and it's floating. Well, what happens here is, I'll use blue, there's a downward force of gravity. We could call it F sub g, which is the weight of the particle, trying to pull it down, but it's being suspended or levitated in a sense by the electrical force that's up, F sub E. And if it's just floating there stationary, what I know is that F sub E must be equal to F sub G. Once again, you go back to your equation sheet, or you've practiced these enough to know this, and here's one of the beauties of parallel plates. You can use the equation, the definition basically, E equals F over Q. The only thing we can't use are point particle equations. This is a general definition that applies to all electric fields. E equals F over Q. Or in other words, F, electrical force, that's F sub E, F due to an electric field, equals EQ. We'll use that fact a lot. We also know that W equals mg. W is the force of gravity, F sub g. So what we'll do here is we'll be subbing into the blue equation. We'll sub in this and this for the quantities over there on the top. We have E times Q, and that's not E sub Q, that's E times Q, equals M times G. And we're looking here for, we're given E and Q. We're looking for charge. What we're looking for is Q here. So I'm going to rearrange this first before I do much other substitution. In other words, Q is the only unknown that I have, because I've read the problem a couple of times. You'll see here in a second. I'm just moving the E over. So we're looking for Q here, the charge that's on that floating particle, so to speak. So Q, the charge on that floating particle, is the mass of the particle, 1.11 times 10 to the negative 15th kilograms, that was given, times G, which is 9.8 always at the surface of the Earth, divided by E, which is 34,000. Kilo was 1,000. So Q comes out to be 3.2 times 10 to the negative 19th coulombs. That's the charge on that particle, that floating particle. What it says in the problem, though, is how many excess electrons is it carrying. It's probably got lots and lots of electrons, but what's the net charge? Well, the net charge is 3.2 times 10 to the negative 19th, but how many electrons on that? Well, most of us can probably see it without actually writing it down, but if I just take that total charge, 3.2 times 10 to the negative 19th coulombs, and divide by the value or charge of one electron, 1.6 times 10 to the negative 19th, how many electrons does it take to make 3.2? Well, the answer is it takes 2. The answer to the problem is 2. There's 2 excess electrons on that charge. Now, one of the things here with this problem, it's actually a very famous experiment done by Millikan. It's called the Millikan oil drop experiment. What he did, and it probably took him months, if not years, to actually perfect this and to actually figure it out. We did it here in like 3 minutes, 4 minutes. But he atomized or used like a spray bottle, and he sprayed little small droplets of oil between 2 charged parallel plates, and he knew what the charge on the parallel plates were. In other words, he knew what the electric field was and the rough size of these little oil drops that he blew into this space, and he knows that gravity is 9.8, the acceleration due to gravity. So he could figure out the charge on these little spheres. It was a little bit more involved than that, but that's pretty much the idea. And he did this experiment over and over and over again, and he would get answers like this. He would get this like, I'll use red, like 3.2 times 10 to the negative 19th coulombs for his answer. Then he might get like, say, 6.2 times 10 to the negative 19th coulombs. And then he might get 4.9 times 10 to the negative 19th coulombs. He would just do this over and over again. I'll just put some other numbers down here. 3.3 times 10 to the negative 19th coulombs. He just keeps doing this over. 14.5 times 10 to the negative 19th. And the numbers I'm putting down here, believe it or not, they're pretty clean. In other words, you write these numbers down, you keep looking at them and analyzing them statistically and so forth, and you try to come to some conclusions. You know, is there a pattern here? You might try to graph it, so on and so forth. And if you look at these long enough or do the mathematical analysis in this particular case, what you will notice about these numbers, they're all basically multiples of 1.6. In other words, there's a common factor here. That's what he noticed. The common factor of all these numbers, basically in red, is essentially 1.6 times 10 to the negative 19th coulombs. Essentially, this was his conclusion that the charge, the fundamental charge, is the 1.6 times 10 to the negative 19th coulombs. That's the charge on the electron. So in conclusion, one more time, most of the problems we'll be doing will be in one of these two categories. Either it's a fairly obvious point particle problem like example number 1. If not, try to do it like numbers 2, 3, 4, or 5 where you have parallel plates.